Yeah, I mean, can you print the slide out for a second? The deck, or at least my slides.
Yeah.
I wonder if you can do that or not. Okay, don't worry about it. So I'm talking till slide 10, yeah.
Okay.
You just print up to slide 10. Watch, I don't know what happened to it. Stop working.
What?
Battery.
Oh, no.
Wait, we only have 3 minutes left.
I know. I have to hit start. Okay, Thanker.
Okay.
We're going to put you on mute for a minute and just have the people start logging in.
Okay.
Attendees still on hold. Okay, start broadcast.
The broadcast is now starting. All attendees are in listen-only mode.
Hello, welcome to our DISYS webinar today. We're going to give a few more minutes for people to log in, and then we'll get started at 12 o'clock. Thank you. Welcome to our webinar. This is Angela Brooks. I just want to give everyone one more minute to log in, and then we'll get started. Thank you. Hello, thank you for joining our webinar today. My name is Angela Brooks, and I want to just welcome you. I wanted to also say good morning or good afternoon, depending on your time zone. I'm the manager of global marketing at DISYS, and today's webinar is leveraging Hadoop for big data processing. Thank you for taking your time out this afternoon to join our webinar today. We have two incredible speakers, and we're going to jump in and start discussing this hot topic. To jumpstart our discussion, we wanted to give you some feedback on the questions that you answered during the registration survey. You may remember that our first question was, which big data result are you most interested in achieving? And as you can see, the top choice here was set up and configure your environment at 36% and derive insights about your data at 23%. Our experts, Amar and Sankar, who are with us today, are going to be talking about these two topics specifically. Additionally, we asked you a second question, and we said, what is your time frame for implementing a big data solution? Well, I think it's clear that 66% of you said not sure, but there are 9% that are already on their way, and the other 25% of you are going to get started now or in the near future. Amber and Sanker will give you the foundation today to get your big data solution started. I'd like to formally introduce Amber and Sanker. Amber is DISYS' Vice President of Global Services and specializes in big data and cloud enablement. He has more than 20 years of experience in the emerging technologies field, and at DISYS he leads our company in developing new and innovative service offerings that are managed and delivered globally. Amber has served in numerous executive leadership positions with large corporations and is quoted frequently in Businessweek, CIO, and other technology publications. Amber, would you like to say a few words?
Thank you, Angela. Looking forward to talking to the group here, as well as the questions that will come up during this presentation.
Thanks, Amber. Excellent point. We'll talk about questions in 1 minute. Sanker is a big data architect and Hadoop expert with more than 20 years of IT industry experience, focused on mobile computing, cloud computing, and of course big data. He was instrumental in developing the Zeus mobile platform at one of the hottest mobile startups in Asia. Hadoop is a DISYS fellow, and what he does is help DISYS with our research and development as well as proof of concept work for the Hadoop space and our Hadoop customers. Sanker, would you like to say a few words?
Hi, Angela. Thanks. Thanks, Amber. So, hello to everyone on the call, and I appreciate you are taking the time out and attending this webinar, and I hope you will find this webinar pretty interesting as we go forward.
Thank you, Sanker. Before I turn over the webinar to Amber and Sanker, I just want to let everyone know that you can ask questions via the questions feature on the control panel on the right-hand side of your screen. We will answer at the end of the webinar. Also, we are recording today's webinar so that if you'd like to watch it again or pass the link to friends and family, you can we'll be sending you a link of the recording within 24 hours after the webinar is completed. Okay, everyone, thanks again for joining us today. Thanks also to our presenters. Amber, take it away.
Great, thank you, Angela. As part of this presentation, we'll sort of quickly introduce you some trends that we've been observing in the market, and then Sanker will sort of go in a little bit deeper into identifying the types of big data and how you categorize them, go into a little bit more detail around Hadoop, and then talk about how do you actually implement Hadoop within your enterprise. And then we'll sort of look at answering any question that you have at the end of the presentation. So from a trends perspective, I'd like to sort of cover two things. One, broadly from an industry perspective, over the last several years, we're actually seeing pretty much exponential growth in the data that is actually now resident within the enterprise. So a couple of years ago, numbers like terabytes were pretty daunting, but now most of the enterprises talk about petabytes and even exabyte level data. What we're also sort of finding is that some of the industries tend to obviously have a lot more data that gets collected and that needs to get processed. Financial services industry is obviously one of them. And then the other one that's sort of coming up and becoming more reliant on their data is the healthcare industry. Not only do they have a lot of data, but they also sort of have government regulation and mandate on the fact that they actually do need to process that data for billing purposes as well. The other sort of trend that's kind of emerging is the fact that the internet itself is not necessarily just composed now of computing devices, but now consists of sensors, and a lot of sort of machine-to-machine communication as well. So we're seeing, pretty substantial increase in the number of connected nodes on the internet, which are not necessarily computing elements or personal computers, but other devices that are generating lots and lots of data. One of the areas that we had, we've spent some time looking at is really on the retail side, where the point-of-sale system, generate tremendous amount of data that needs to then get matched up with an enterprise's inventory system, as well as, what the retail organization may be seeing from their website and e-commerce purchases. So a fair amount of data being, aggregated through these different devices that are out there. What we're also sort of seeing in the market is that essentially, if you don't do anything with the data, that's a pretty sort of large corporate asset that is not being fully utilized. Some of the new term that's actually coming up in the marketplace is the term of data equity, and really companies that can unlock the value of all the data that they have within the enterprise can derive sort of more value and essentially add more equity to their organization by leveraging the data that they have within their existing enterprise. And one of the ways that, we will be able to leverage data and be able to tap into these vast amounts of data is through technologies like Hadoop as well. And then finally, if you sort of look at it broadly, there's a study done by McKinsey at the beginning of last year, which actually sort of did some very interesting analysis in terms of leveraging big data and how that can actually impact the actual productivity within particular sectors. So again, we see that there's a pretty good big data potential, and being able to leverage big data in certain enterprises that can actually impact productivity. And we see that again within the healthcare provider space. We see that within the financial space as well, and then in the manufacturing sectors as well. If you were to look at some more sort of actual use cases in these industries, from a capital markets perspective, you see a lot of high-value transactions that are happening, and what we want to be able to do is do consolidated risk analysis across those data sets. Within the telco space, what we're also seeing is, finding better ways to leverage telco call volume data and pretty much all the different call records that are being collected. The one thing that we've had some opportunity to spend some time on is actually looking at call volume data, sort of being able to map that to certain transactions that happen within the healthcare industry, and essentially coming up with algorithms that can do fraud detection as well. From a digital ad services perspective, you pretty much all the ad campaigns that are being constructed by either retail companies or other sort of companies tend to be multi-channels. You're doing Facebook campaigns. You may be doing sort of placed or sponsored stories on Twitter. You may have ads placed on website, and then you have ads that are sort of being placed as search ads on Google, and then obviously your traditional advertisement that you've been doing on sort of television and the print media. Aggregating all that information and being able to sort of process it together is one of the big sort of use cases that we're seeing in the marketplace as well. So let me sort of just kind of summarize by saying that a lot of exciting things that are happening in different industry sectors and how they've been utilizing and leveraging the enterprise data, and a lot of it is actually based on utilizing technologies like Hadoop. So let me turn it over to Sankar to talk a little bit about what are the different types of big data, how do you categorize them, and then how do you bring Hadoop to sort of allow you to leverage and optimize your existing data set. All right, Sankar, we'll will pass over the control to you.
Okay, Sankar.
Thank you, Amar. Yeah, so thank you, Amar. I'm going to be spending the next 30 minutes, 35 minutes on three important aspects. One is you have just heard that there is a lot of big data and there is a lot of things happening in the industry. So how do we identify and categorize the big data, and then how do we bring the big data context into Hadoop? What is the motivation for Hadoop, and how do we typically run Hadoop from a very high level? And then I will talk a little bit about how to decipher the information when we process big data on Hadoop. And then we have some recommendations, and I believe we will have some questions and answers, a Q&A session before we summarize and end the call. So when in terms of categorizing the big data, there are primarily three ways and to categorize the big data. Before that, it's important that we understand the sources of big data. So this is illustration of some of the key sources of big data. So if you look at it, there is a lot of data that resides in the enterprise, which is typically called as dot data by Gartner. So the reason being that either it is not used internally, or it's not being acquired or actively processed inside the enterprise. Then you have commercial sources of big data, which can come from sensors and mobile devices, which can be part of the whole transactions inside an enterprise. And it can be a set of data that comes through various interaction or touch points from partners, employees, customers, and suppliers through various means, from mobile or from the web, or from traditional means such as point of sale terminals, so on. Then we have public data, which can be correlated to, the weather data, the population and economic data, and today we have a lot of social media data that comes from social networks such as Facebook, Twitter, and so on. So what Gartner actually says is, the correlations and patterns are very important actually in order to get it inside the organization or an enterprise, and process that to get the insights and the opportunities for transformation from processing this combination of various types of data is pretty significant. So when we do the categorization of the big data, primarily or broadly across the industry today, it's categorized either by data volume, or by the variety of data, or by the velocity of data. So big data doesn't really mean that it just has a huge size to be categorized as big data. So these are the various ways to categorize. For instance, a company, an organization would typically want to optimize a capital investment based on a couple of petabytes of data information that they have inside the organization, which is already present, but which has never been used. So if you look at that aspect, then it becomes more of a volume-based processing, from where an organization or an enterprise wants to derive insights or value. Another organization may want to analyze the fuel consumption, telemetry, weather records, you know, to optimize transportation or logistics, which means that inside the organization there could be several types of data or variety of data that can be present in various volumes, and if you have to combine that and then process that, the complexity involved in that to process is pretty significant. So that's another way to categorize the big data. The third one is the data velocity, which is about the speed with which the data enters and exits an organization. So this could relate, for example, to hundreds of thousands of records being processed in near real time. For example, an organization may have an online web-based CRM application which may have hundreds or thousands of comments and questions being asked online, and this could translate into thousands of messages per second or millions of messages even, depending on the size of the organization. So the velocity of the data here, has more significance than anything else, and that's another important, categorization of big data. So if you look at the dimensions, the data volume, if we categorize it by data volume, it could be typically, terabytes or petabytes of data. So it's pretty much a relative term. So one organization could have hundreds of terabytes, the other organization could have petabytes of data. So it depends on the problem at hand, and and there is no one single definition on the volume of data. So if you look at the variety, you could have structured data, you could have unstructured, semi-structured data, or a combination of all that needs to be processed to yield, some kind of value out of the various types of information that is present. In terms of velocity, it could be either streaming or batch data, so there could be a lot of batch processes, or it could be a lot of near real-time streaming data that is coming inside the organization, or a combination of both that needs to be processed. So these are the these three form the key elements to categorize the data in terms of volume, variety, and velocity. So to delve a little bit more, if we consider the looking at the data set considerations, so what are these? What are the kinds of data that we are talking about? From a big data context, primarily there is a lot of unstructured data typically that organizations have been dealing with, as well as structured data and the combination of both. So this slide is about making you to understand a little bit about the data set considerations based on variety or and volume. So if you look at the two key data set considerations are unstructured and structured. So within the scope of the unstructured data, so we can call data set to be either intrinsically managed structure or intrinsic unmanaged structure. So what intrinsic managed structure means is in a data set, intrinsic means that it's part and parcel of the data, and it is explicitly described in a certain format. So let's say if we have an XML file, so XML file is not a really structured data which has a schema or a data definition, but it has it's a file which contains information, some information about the data. So there are other files like CDF and other exchange format files, which are used in business, which typically represent this type of data. Then we have intrinsic unmanaged structure, which is typically content in human language. It could be speech, it could be some text file, and it can only be understood by some semantics and parsing the data. In terms of the structured data, we have extrinsic managed structure, which is the structure is not a part of the data, but it is defined in a schema actually. So we define, for example, in RDBMS, we define the schema and then make the data to comply with the schema. So in the extrinsic unmanaged structure, we have typically non-schematic databases like key value stores like for example, MongoDB or DISYS are a couple of examples where the data is typically managed in program code than through a schema. So if you look at, so having said that, if you look at the data variety, the variety of data could be that's one of the important considerations, or the categorization that I just said. So the data variety could be very wide. So especially if you look at the unstructured data, which is being considered for processing, or where most of the big data comes from. So it could be a lot of video files, it could be image files, it could be audio files, it could be different text files. So that that can be and it could be totally unstructured, and it could be structured only partly or semi-structured. So this slide actually shows. This is a slide from McKinsey Global Institute that indicates the kind of structured and unstructured or semi-structured data that's found across various verticals. So you can find that some of them have a lot of video, audio, and text, but some of them only have text files. So the third important categorization, which is the data velocity, is all about processing data, incoming and outgoing data at very high rates. So what does it mean? So a couple of examples here, as you can see. If you look at Instagram, I just wanted to take a couple of examples. One is Instagram, which processes 5 million photos per day, which is pretty huge. They have like something. They have something like 575 likes per second, 81 comments per second, which translates into high velocity or high speed data that needs to be captured and processed. And similarly, if you look at Twitter messages, you can see there are millions of messages processed per day, and so that basically represents the kind of velocity of data that we are talking about. So inside an enterprise, this could be, for example, a lot of web streams, click streams, or it could be firewall data, or some kind of security data, which could come at the similar velocity. So if you look at the dimensions for big data, basically there is a need to process extreme information management. So this is the Gartner's depiction of the big data. So one has to deal a lot in terms of complexity, volume, velocity, and variety, and apply different or appropriate technologies to to process and get the value out of the data. And it needs to be intentionally managed across these dimensions to meet the challenges of deriving the value out of the data. So when we look at the technologies to process the data, so we need a new generation of technologies and architecture designed to, and they should be designed to economically extract value from very large data volumes or high-speed data, because we're talking about very complex challenges, which has to be which cannot be uneconomical. It has to be economical to the extent of deriving the data, deriving value from the data. And the other important factor is a lot of organizations today consider the dark data, which is typically unused or discarded data, which is being in which they don't see any value today, but there are initiatives to process that and discover information and get value out of that. So if you want to use a technology, to process the so-called dark data, so it cannot be a expensive technology to process, to explore, value out of that. And the technology should also enable high velocity capture, discovery, and complex analysis. So if you look at the associating the types of data, the data, big data, the process with which we categorize the big data, applying the criteria in terms of volume, variety, and velocity. So Gartner says that based on some measures across the industry, typically in terms of volume, anything greater than 100 terabytes is something which we can really call as a big data, because there are a lot of companies like Facebook, which is already processing data at the volumes of tens of petabytes. I think Facebook has crossed 20 petabytes, so in relative terms 100 terabytes is a smaller one. So in terms of high speed streams, we need to look at what is the data velocity, or based on the data in motion, or the events or messages that is being processed in an organization, is something which is an important criteria to declare that it is big data. So essentially, we have two important segmentation of the criteria for big data evaluation. One is the big data at rest and the big data in motion. So the big data in rest is pretty much a static data, which is already present in the form of files, and big data in motion is something which is a streaming data. And Gartner also says that if an organization has data sets growing at a rate of greater than 60% a year, so that could be criteria to declare that we have big data inside the organization. So when we look at big data and processing the big data inside an organization, so I want to touch base on quickly on the typical problems that we encounter when we process large scale or big data, large volumes of data, or data with higher velocities and traditional computing systems, and then talk about Hadoop. So typically the problems with the large scale computing is so for many decades the focus was in terms of raising the CPU, making the CPU faster, and then increasing the RAM size. And mostly the focus was to improve the performance of single machines. So if you look at the processor-bound computing, so which has some challenges and limits when you look at the way that you have to process big data. Secondly, when you look at distributed systems, there is a lot of complexity. So there are things like data exchange, synchronization. So you can have hundreds of thousands of machines which has to work independently to solve a common problem. And when you design distributed systems, basically there are issues that you come across in terms of synchronization, the ability to work across hundreds of machines or thousands of machines with a finite bandwidth. Then there are complicated temporal dependencies, especially when you look at streaming information or data. Then there are difficulties dealing with partial system failures. Let's say if 10 machines or systems fails, then what's the outcome? Do we expect, or what do we expect? Will the data be, will the information be processed in a deterministic way? Is a question. Then the data is pretty much stored in storage area networks in a typical hub and spoke architecture. And then at compute time it is copied to nodes, which also has limitations and the challenges. And in these kind of systems, developers have to spend a lot of time designing for the failure, to handle the failures than to really focus on solving the data processing. So as we move into the data-driven world, where we are already talking about volumes of data, huge volumes of data, or data with multiple touch points of data with streaming data. So we are going to more and more deal with a lot of challenges. So the modern systems, have to deal with ever-increasing data, and more so, most of the organization will realize, or already they are realizing that data has inherent value and cannot be discarded. That's the reason why Facebook, Twitter, Orbitz, eBay, and a host of other companies have taken all kinds of data to explore, the value, to explore what it contains, and then derive value and insights for their business. And many organizations are also generating data at the rate of terabytes per day. So we are moving into a totally different world for which the distributed systems and the technologies play a very critical role to address the requirements. So when we look at the bottlenecks and processing this data, these are some of the bottlenecks as you see here. So typically, let's say, if you look at the standard, machines that you have today, you have, for example, 22 minutes to transfer 100 GB of data at 75 MB per second, with the DISYS. And most of the data is buffered in the RAM and then transferred, and you don't have a capacity of 100 GB RAM today. It might be there, but not, the things are coming up. Then you deal with parallel, the parallelism, when you have a huge data set, how do we split the data? How do we ship the data across distributed systems for processing? And so when we have hundreds of machines, if some of the processes inside the software layer fails, or if there is no consistency in terms of the handshake between the machines, so how do we handle that? These are some of the major bottlenecks that many technologies and products have been facing. So the objective is, can we do a graceful degradation versus entire system failure? So you can't afford to run a data processing batch for let's say for 48 hours, and then after a day or so something fails, and then you have to roll back and then start processing again. That's something which is indeterministic, and that really doesn't solve the problem. Then how do we take care of the component failures at the execution time and have predictable job outcomes? And one of the key things is how do we scale with the volumes and complexity of the data. So adding load to the system should be graceful in terms of the performance. You cannot take you shouldn't have a distributed system which poses a problem in terms of taking the additional capacity. So increase in resources should support load capacity. So, which means when you add new disks or RAM, so seamlessly they should scale up.
Sankar?
So,
it's Angela.
Hello?
Hi, it's Angela. I just wanted you to be aware of the time because we're running low on time and we need to cover the next several slides about Hadoop very, very quickly.
Okay.
So that you can talk about the technical. Thank you.
Yeah. So a new approach is needed to solve all these problems. So Hadoop provides a new radical approach. So if you look at what is Hadoop, it's open source software framework, which is a scalable and fault-tolerant one. It's the core components of Hadoop is HDFS, which is the file system, and the MapReduce framework, which allows huge distributed computations. So the core concepts of Hadoop, if you look at the challenges that I talked about, it is designed to meet all the requirements for reliability and scalability. It's a data-centric MapReduce programming framework. So MapReduce is a parallel processing framework, and you actually, when you say data-centric, you move the, so the computation happens at a place where the data is already there, and if you are able to chunk big data, a large volume of data, and then move it across to different machines and make the computations happen in those machine, which is typically called as a cluster, that's how we were able to produce solve the bottlenecks and using the MapReduce framework and process the large complex data. So the core concept involves shared nothing architecture, which means that each system in a cluster will work independently of others, and it doesn't require much of communication. And the open source Hadoop project has a lot of sub-projects, which is HBase, Hive, Zookeeper. I'll touch upon this in the next slide, Chakwa and Avro. The goals of the Hadoop is make it scalable, solve petabyte scales of data on thousands of nodes effortlessly, and at the same time provide economical and reliable, bring economics and reliability into the the whole way of its working or deployment. So I'll give a high-level overview of Hadoop software stack. So we have the core component in Hadoop is the MapReduce framework and the Hadoop file system. We also have other frameworks, Hive, which is a data warehouse, Pig is a data flow framework, and it's also a language. HBase is a key value store, database. Chakwa is a log analyzer. And so it's just being used in a combination and depending on the type of big data problem that we solve. HDFS is a file system developed in Java, which has basically which is implemented in a name and data node type of a configuration. and it's basically a namespace in which we operate HDFS. The next key thing is the MapReduce paradigm. MapReduce is a parallel processing paradigm. So typically it has the data input is mapped. It's as a key value pair. It goes through a shuffling, which is typically sorting kind of work, and then you have reducers which reduce the problem. So basically, MapReduce maps the data, and then it distributes the data, across the individual systems in the cluster, and then each one of them, works on the data independently. So, and then the name node collects the data and then processes the results. So this is a good example. So typically, just to quickly look at on the left side, you have a temperature data, and what we want to find out is the maximum weather from the max weather from a weather service provider. And what the map program does is, it basically extracts the year and that temperature, and then you have the shuffle program, which basically sorts the group key value pair, and then it creates a list, and then which is reduced through an iteration process to give the final output, which is the maximum temperature for any given year. So this map and reduce process is distributed across the machines in a cluster, and the same process goes through in every cluster, and then the final results are collected and presented back. So if you look at the high-level processing, so we have what we need to do is to take the data input and then split the data in HDFS as blocks, then map the tasks, and then we have a master program which allocates the works to the reducer or data nodes on the cluster, and then hundreds of machines or thousands of machines process the data and generates the output required to solve a typical big data problem. So the common factors that we end up in big data processing is the nature of data and the nature of analysis. So it could be complex data, it could be a lot of data at once, a lot of batch processing. The type of data analysis could be very broad. It could be collaborative filtering, text mining, pattern recognition, predictive analytics, so on. So based on these are actually implemented as algorithms. So you have a lot of algorithms implemented to solve specific types of problem today. Common Hadoopable problems that prevails in the industry today are modeling true risks, coming up with recommendation engines based on specific input data. For example, e-commerce data, buying patterns, point of sale transaction analysis, threat analysis, basically based on network data, for instance. So powered by Hadoop, so you can see some examples of some of the large deployments. So you can find this information on the Hadoop's Apache website. So companies, these are companies which have pioneered the use of Hadoop for processing complex and large sets of data, as well as what do you call streaming data, high velocity data. So this is a snapshot of screenshot of how Hadoop is being used at Facebook. They use HDFS for staging. Staging is a very important aspect for which HDFS is used. And then Hive is a data warehouse where large sets of data are aggregated, and then the value out of the data is extracted through appropriate means. So how do we, so if you have to look at putting Hadoop to work for you, so I would like to mention 5 easy steps to big data processing. When I say 5 easy steps, these are high-level steps. So the first one is identify the big data sets evaluate the Hadoop workload, determine the Hadoop infrastructure, integrate with data sources, and process the workload. So this is the high-level approach. Of course, a lot of things needs to be done in a realistic manner, depending on the type of problem we solve. So the typical Hadoop topology is something like this. You have different types of data sources and different types of touch points, and you have a Hadoop cluster which processes the data and then sends the data to business intelligence applications for analytics and then presentation. So identifying the big data in your organization is the key thing. I think it's the most critical thing when someone embarks upon big data initiatives in an organization. So the characteristics are typically very large distributed aggregations of loosely structured data, terabytes or petabytes with millions of people using something, and very complex data structures involved in that. Look, if you have to evaluate, the next step is to evaluate the Hadoop workload. Workload can be evaluated using data staging, online archival, transformation engine, data mining, and different types of work that needs to be done. These are some examples. So workloads really matter because there is going to be a lot of data that needs to be processed. There is going to be a lot of streaming data that needs to be processed, which basically has to do with IO intensive or CPU intensive characterization. And based on the workloads, we need to determine the Hadoop infrastructure. So the typical questions are, should I go for in-house or cloud-based deployment? What is the computing power needed to process the data? What is the cluster configuration? What is the data processing framework to use? And so on. So these are some of the important questions. And then once we have some answers for the questions, then we decide, one can decide on the Hadoop infrastructure either on the cloud, for example, on Amazon AWS, or it could be an internal data center using, for example, Hadoop distribution from a company called Cloudera, which is pretty much a leading company. And then, so this typically involves sizing the workload type based on whether the company has to do IO intensive processing or CPU intensive processing, and then size the machines and clusters. The typical recommended approach is in Hadoop, most of the people so far have ended up doing a lot of testing and then improving their Hadoop architecture and the deployment, production deployment. So it's always best to invest in a balanced Hadoop cluster, which means balance in the IO and CPU intensive tasks, and which can offer better performance over a period of time, and not go with the big bang kind of approach. Do a lot of monitoring, do performance testing and validation, and then optimize the cluster, which could be augmenting the cluster or changing the type of machines, etc. So the typical Hadoop size cluster, cluster sizing. So how do we do this? So this is a very general guidelines. So of course there are a lot of things to be taken into consideration. So for example, if you want to process, the simplest way to determine the size of the cluster is, if you want to process X amount of data, here it is represented as 5 terabyte of data on a specific Amazon machine size, which has 1690 GB of disk space. So we end up with the calculation of 15 numbers of machines of a specific machine type to process this much of data, of 5 TB. So it basically gives just a pointer, but however, there are a lot of other considerations that needs to be made, which is out of the scope of this presentation. So this is a screenshot of how we, configure Hadoop cluster on Amazon cloud. So typically, we have the Amazon Elastic MapReduce console to select the type of the Hadoop framework on which we need to operate. Either it is Hive or HBase, and how many number of machines we need to have, and configure a whole different type of things to start the cluster. The other important factor in the Hadoop enablement is the integration with the data sources, which is it's another critical part, which also takes a lot of time. So it could be from databases, streaming data. It could be from a cloud storage. So we have different tools for doing that, and also built-in libraries within the Hadoop frameworks, which is represented here. So the popular ones, for example, are Apache Scoop for integrating with RDBMS, Flume for unstructured log files, Kafka and S4 or some other things which are coming up in the industry for handling streaming data. And then once we have the integration of the data from different types of sources into the Hadoop cluster, then we process the workload on Apache Hive or Pig. Depending on the type of the problem. Let's say if an organization has to create a data warehouse, or the size of the data is huge, then we go for Hive and then process the data. If it is just a typical extract, transform, load kind of a data flow kind of a problem, then we select Pig for processing. Cascading is another framework, which is another type of Java-based framework, which is used widely in the industry today for data flow problems. So this is something which we have to keep in mind, when we select the workflow processing on Hadoop. This is a slide on the DISYS Big Data Processing Framework. So the typical process, typically we have process architectural references, frameworks, and best practices as a part of the whole framework. So which typically does, handling of the entire life cycle of processing of big data on Hadoop. So right from acquiring the data from raw sources, raw data from multiple sources or from RDBMS, to data ingestion, to MapReduce processing using different frameworks, and then moving that to upstream analytics. We use different types of tools and best practices as a part of that. We also have a Hadoop orchestration framework that automates the data, the whole processing life cycle of processing. So this is a slide that depicts that. So we have. So what we do is when we start a Hadoop cluster, we automatically initialize the cluster, or so to say bootstrap that. We extract data depending on the type of extraction methods that we should follow to solve a data processing problem. And then we process the data using the required frameworks and algorithms that was developed for a specific problem, and then output that to the sources for further analytics. So finally, if you look at the ways to interpret the results, there is a lot of monitoring that needs to be done on a cluster continuously to interpret results. There are tools, and it's a combination of tools and techniques. So if you look at monitoring, we can monitor running tasks, analyze the MapReduce, job metrics, so on and so forth. So if you look at the kind of questions that pops up, how do we interpret? So typically these are some of the questions. Did all the jobs process without any other errors? Was the processing time within the expected limits? Was the cluster utilization balanced? Did any nodes in the cluster fails, etc.? And then based on that, the problem is identified, and then the jobs are run to run in a predictable manner. So there are tools, for example, to interpret the results. For example, this screenshot of Amazon's Hadoop Web Console. As you can see, it presents a lot of metrics to understand the problems and as well as for optimization. Then there is a Hadoop administration web interface that comes as a part of the Hadoop installation, which is also used for finding out, the checkpoints, errors, and then, because someone can troubleshoot or optimize the cluster, the jobs. Then if you look at an implementation within an enterprise, for example, using Cloudera distribution like CDH4, then Cloudera gives web-based console to monitor, troubleshoot, and optimize the clusters. If you look at yeah.
Okay, let's leave that slide up there so that they can take a look at the bullets that you just had. Go back one. No, sorry. Go forward one. I'm sorry. Forward. Okay, they can read that while we discuss questions and answers.
Yeah, sure.
We just are running low, so we want to just get a couple questions out there to you. One person said, wow, the technology components required seem very numerous. Can you acquire all of this pre-packaged to minimize complexities by the customer? We don't have Hadoop or open source experts on our team.
Yeah, I think the one of the things that we try to do, try to avoid actually when we process big data is the low-level plumbing. So there is a lot of things that typically needs to be put up in the when we process big data in terms of the infrastructure. So one is the approach for many companies have been to look at cloud-based Hadoop infrastructure. So for example, if you look at Amazon, we don't typically deal with the low-level plumbing, so it presents a very high-level and sophisticated interface where you already have all the technology components pre-integrated. Let's say HDFS or PIG or Hive framework, and also if you look at framework like what I quickly presented as the lifecycle management framework from DISYS. So these combination of these two techniques, for example, could give a jump start to start using Hadoop. So if you, as against implementing large cluster within the organization, and also some other things like the reusable components that we have developed in our company helps reduce the development life cycle, and so you don't require a lot of people to to process the to write programs to solve the data. So
okay, thank you.
So I hope this. Yeah.
Okay, one other one said, do you need to know the specific questions you're trying to answer before using the tools, or can you use the tools to help them, to help you discover trends and issues and patterns in the data?
Yeah, so my answer would be that there is definitely a need to understand at least the type of data that you're going to be dealing with. So I think we touched upon the type of data in terms of the volume, velocity, or variety. So, and then the second one is to look at how do we bring the data and organize the data. So once we have this inside the Hadoop cluster, and I think most of then it's just a question of what is the best framework to apply on the data. So that's a relatively easier one. I think the complexity is more in terms of finding the what do you call, identifying and categorization, categorizing the big data.
So you do want to know what questions you're trying to answer first, correct?
Yeah, absolutely. Yeah.
Okay. Okay, one more question, and then we'll just close out. This one says, are traditional DBA and business intelligence toolset skills easily transferable when working with Hadoop architectures?
So the answer is yes and no. So it depends on the type of tools and technologies that we deal with when we do big data processing on Hadoop. For instance, Hive is a data warehousing framework which has the which is very similar to the SQL. So Hive is based on Hive query language, which is sort of similar to SQL. So, but still there is a need to understand the fundamentals of how the Hadoop clusters work, HDFS. But someone who already knows SQL can quickly ramp up on learning HQL. So in a similar way, PIG is a framework which is a data flow language. So anyone who has been doing functional programming in C or Python will be able to appreciate and learn PIG for data processing. So there is definitely a scope for people who already know SQL and who have been SQL DB or a developer to get faster than others who probably don't know anything. So there is a scope for that. Angela?
Sorry, Sankar, I was on mute. We are running a little over, so we will address the other questions by getting back to those individuals that ask questions. We do want to thank everyone for their time today. Thank you, Sankar, for your time today in presenting this valuable information. And if there are other topics of interest to you, I've put a slide up that gives you some web links to some of our past webinars. As well, you will receive an auto email from the system that has a web link to this webinar, so you can watch it again, listen again, or pass it on to others. Sankar, would you like to say anything in closing?
Yeah, thank you, Angela. Thanks everyone for attending the webinar, and I hope you found it useful. So thank you again, and have a great day.
Okay, thank you, Sankar. Everyone have a great day. Thanks so much for being with us today. Bye-bye.